Srini, a small interjection from my side. Uh, could you also maybe throw some light on maybe the crossovers which are used in loudspeakers? Essentially, there are also filters. Like, okay, Sandeep, you have a question. Can you maybe just unmute yourself and ask?
Yeah, hi Karthik. See, I have a question. I just want to understand. Okay, you've been talking about the harmonic structures and all, right?
Yeah.
Can you hear me?
Yeah. Please tell.
Yeah. So in this, I just wanted to know that what it takes to get a uniform decay in the harmonic structure. What exactly it takes to do that? I mean, for example, let's consider you have your fundamental let's consider 0 dB and your second harmonic is at taken at minus 20 dB. Consider just an example, and the third harmonic sitting at about another 20 dB less, like that. It's like a curve which is going like a linear decay fashion, something like that. So what it actually takes to get that point. And the reason why I'm asking, because no matter this is something which is observed in most in the valve preamplifiers or valve tube, the small signal to the medium signal tubes with the triodes especially. I understand the fact that the linear characteristics of the tubes, which are relatively more linear, the triodes being much more linear, comparably linear than the pentodes or whatever. So now, in general, in your approach, or the moment we get into the solid state, most of the curves look more like a pentode curves, and you do expect some crazy harmonic proportions which are kind of which are not in your control in the sense. So now what is that you would tell when it comes to the proportionate harmonic structure to be achieved if I want something? Because if I take a conventional preamplifier where my load does not consume a lot of current, and much of the stuff works in a pure class A and relatively more symmetric, and I get a relatively proportion harmonic structure like a dominant second harmonic, and then you have a third harmonic which is in a relatively proportionate way, which does not alter the yeah. So now what it actually takes to get to that thing, if I want a like a fourth harmonic to be in a proportionate ratio with the second, and then the third as well. I would say the third as well. That's what is the tricky part. What do you suggest? I mean, from the system perspective. Yeah, you got what I'm telling. I mean, I'm not talking the circuit level. I'm talking in the generic process. What it actually takes to do that.
Yeah, the moment you have a frequency response, right? You no longer have. So you're always talking about a linear system. The moment you have a frequency response, you're always talking about a linear system. So it's not. So when you're going into the nonlinear portion of your triodes or diodes, you cannot have a frequency response at all there. So you cannot talk in terms of attenuations. You cannot talk in terms of frequency response. So what happens when a uniform drop in your frequency response? You typically do not want. So it's like you have a pole on a transfer function that occurs much before the attenuation starts. And you do not have any more poles in that period in which it is attenuating. So suppose I have a first filter. Suppose I have 1 upon s plus 1. Yeah, that means that from frequency of 1 radian per second, it will start falling down.
Okay.
And then you will just have a 20 dB per decade slope throughout.
Okay.
So maybe I can just show it to you on this Excel file. Just share this Excel file. Yeah. So if you see here, so now suppose I kind of enter this as b is equal to 0, and I just put s plus 1. Yeah. So this is this will just plot 1 upon s plus 1 for you. And so this, if you look at this particular curve here, so now it kind of begins to fall off at so it begins to fall off at around 0.1 here. Yeah, and then after that, your thing is just going to
Yeah. See, the point what I'm asking is all about not in the filter, because I'm not looking at the filter perspective. I'm talking about a conventional Fourier perspective. Like, I mean, for example, if you have a system which is asymmetric, you're expected to have a dominant third harmonic, which is actually a bad sounding, at least in terms of sound, and on the multiples of the the odd order harmonics, which if they take the dominance sometimes, and which happens in amplifiers, which happens in the preamps and stuff like that. So
happens
So,
is that
yeah.
why that happens is that you start operating your amplifiers in the go closer to the saturation region of your amplifier.
I agree to a level, because I agree. What you said is, yeah, when it is getting saturated, you start to see a lot of the bad nth harmonics coming into the picture. I agree that. But I mean, the point about you would not be running an amplifier in a pure class A mode all the time, without the crossover distortion. You don't be running. So then you do expect the reason why I had to ask you this, because I'll tell you the reason why I had to ask you this, because if we have a disproportionate harmonic structure, then you would lose the actual natural harmonic profile of the instrument which is being played.
Yeah. So what you would do in this kind of thing is that you would suppose you have a certain nonlinearity in a system.
Which is non-linear most of the cases. Any case you take a
Correct.
basic transistor itself is non-linear. You put a feedback, you put whatnot, you put a servo, you do everything to get it corrected to a level. But all about it, the thought, the kind of, is it like a symmetrical circuit system would eventually avoid that harmonic profile being relatively more linear decay?
So if you ask that to me as a control system engineer, yeah, so what you would then do is you would try increasing the linear region of the system. So that can be done by adding certain nonlinear filters. You have certain nonlinear feedbacks that you can in order to increase the linear range of the system, so that your system begins to appear linear for a larger range. Especially when you want a larger linear operating range of a system, you can kind of do that by adding nonlinear filters to the system. So it's like you add another nonlinear component that kind of cancels out the nonlinearity that's there in the original component.
So technically, you want to make something opposite of the whatever the problem which is being created and cancel it out. Technically,
that's feedback, right?
Like
right.
a push
So you have
right?
Right. So you have various techniques for this. You have something called as feedback linearization.
That is
You
standard, yeah. But I mean, see, the point is about agree. When you say feedback, there is a very clear notion of having a substantial feedback in a system. Or let's consider you have an amplifier with an extremely high open loop gain, and you start to put a lot of feedback, and it starts to sound very constrained. And that is something like putting a number of transistors and making the circuit too complicated with a lot of gain, open loop gain, and then you're putting your feedback, and then you start getting the extremely low output impedance and high damping factor, reducing distortion, everything. But here the problem is not about that. The problem is about, I agree what you're telling. See, feedback is a problem. I mean, you consider it as a process, because see, when it comes to ears, when it comes to especially audio part, but when it comes to conventional control system, feedback is ultimate, because that's where you get the precision of placement or precision of whatever that you're trying to control. Now, the challenge here is how to get all these things without using, the kind of feedback, which is a tougher part, which I understand what I'm asking about. It's like making something simpler, but yet, you should do the job. So that's where my question came into picture here, that when you are using, when we are trying to achieve that sort of,
Sandeep, if I can
yeah.
if I can just interject and let me try to reframe your question. So, are you trying to say that imposing feedback on any system is fundamentally going to have its own demerits? Is that right? And so, is there any
In
other
audio,
way?
I'm not
Yeah,
talking
yeah,
in
yeah, in
other.
audio. Of course,
For
in audio,
example,
it's going to.
yeah.
Yeah.
For
In audio,
example,
it's going to have.
if you have, I'll take a simple example. If you have a printer, or if you have a CNC printer where you're printing a specific a portion with a dot matrix printing, for example, it positions that. And if you have a feedback, like how you usually have it in a servo motors and all, then that is a good thing there, because that gives a much more precise, location of where exactly you want to print. But in audio, the problem is that the feedback is very clearly perceived as a.
It's audible. It's very audible, you're saying.
It's not just audible. It sounds dry. It sounds bad.
Yeah,
That is the
fair enough.
reason why we have the
Is your
feedback.
question that is there any alternative way of trying to achieve the purity without adding feedback? Is that your question?
Yeah,
Relatively
actually,
one way. Yeah, relatively one way. But another way, what I would tell is that what is the thought process goes into not to alter the harmonic profile.
Harmonic structure of the and
Yeah,
basically get the
structure.
purity of the basically get the purity of the signal.
I'll tell you a simple example. I'll tell you a very simple example. This is very interesting. That is, if you take now, I think Srini is he plays violin. Okay. Now you have a violin with certain harmonic profile. If you're pulling one string, if you take the bow and taking that one string, and if you're pulling it, and you have certain harmonic profile of that instrument. Now, if the amplifier is going to change that harmonic profile, then it would not sound exactly the same as what you have been playing or you have been listening.
So it's effectively
Right.
coloring
Exactly.
the
Exactly. And that is very much perceived in solid states than compared to sets.
but how
Because
is that related to feedback? How is that related to feedback?
see, I'll tell you. What I'm telling is that feedback will reduce that natural harmonic structure, whatever it's coming, and it's trying to put it back. And one is trying to correct something which is already left in an amplifier. You take a preamp. When you have a feedback, you're trying to correct something which is already gone. Which is you're at the edge of something and you're trying to put it back into the system. So
Can I say
Feedback
it's
something?
unfortunate. Yeah, it's unfortunate in the audio world that
Can I
is
say
perceived.
something?
Yes, sir.
There is a term called TIM, transient intermodulation distortion. That was proposed by Dr. Otala. So when you have a feedback, when you have heavy dependency on the feedback, there is a time difference between the correction applied and the actual event.
Exactly.
So during that period, it causes intermodulation distortion. So excessive feedback will not sound right. So the idea is to operate, as Srini said, is to operate in the most linear portion as much as possible and use in a minimum feedback for correction. That's what my understanding.
No, exactly. See, now that's what is the point, because when Srini is talking about the what do you call the Fourier transforms, and his approach of putting, because I hardly see anybody talking this advanced in terms of the kind of understanding of a step response, talking about infinities, and this is a subject of of an extreme level. So my thought of understanding, when you're dealing with a lot of nonlinear parts, getting into a linear harmonic profile is one of the toughest things that you can ever imagine to get on. So now my question is not about how you get it. My question is about what is that mindset? What is that the way you think to get to that level?
Okay,
Probably
Srini,
without using feedback. It is a bit more advanced, but I'm just giving you a view.
I'll just maybe slightly rephrase the thing. Srini, do you want to also maybe slightly touch upon, let's say, what is known as analog signal processing, and maybe like I think we just alluded to that a while back before we started the session. So you want to just maybe throw some light on that?
I'll do both of them. I'll also answer his question, and then I'll also talk about analog signal.
Perfect.
The typical
Sandeep,
one thing
yeah,
that,
Srini, one second. Sandeep, just for the sake of the continuity, I'll let Srini take your question. I think Srini has understood the question from Sandeep. Is that right, Srini?
yeah, I've understood the question from
Yeah,
him.
let Srini respond to that. Sandeep, can you please unmute yourself and sorry, mute yourself and also your video, please? Yeah. Please go on, Srini.
Yeah, so typically what happens here is that this is a kind of area of research, not just with audio, but also with other signal processing applications, like say videos or things, where you're trying to design you're trying to design open loop filters at the output, which kind of cancels out the nonlinearity at the input. Yeah, so or the nonlinearity that the system introduces. So this typically uses a lot of machine learning. Yeah, there's a lot of machine learning that is there in order to tune these quantities so that you get a certain good response. Yes, that's. But again, the problem here is that a lot of this tuning happens with certain mathematical quantities that are very objective in nature. So when we kind of do this kind of design, although mathematically we do get the signal that we want, sometimes the thing that you hear does not exactly capture that. Yeah, because yeah, that's something that happens. But the thing that so what you're saying is right. What happens when you introduce a feedback is it automatically makes your system slower, which means that you would have the smearing of sound that I initially said. Yeah, the smearing of sound would be more when you have feedback, because it kind of pushes your frequency response lower. Yeah, if you want to avoid that, you want to operate the device in its full frequency response. Then what happens really is that you can add filters at the output. You can add open loop filters at the output that kind of compensates for the nonlinearity of the system. Tuning those filters is slightly problematic. Yeah, the tuning those filters typically need more advanced math, and they would the thing that people normally use for that is they use AI or ML based things in order to tune those filters. Yeah, so that's what's normally done, at least in the research that I have seen that happens at least in this institute. Yeah, but that is an interesting problem, and probably they may not be a one size fits all solution for this. That these solutions would have to work on particular devices and compensating for those particular devices. Yeah. So Sandeep, does that answer your question to some extent?
Yes, Srini. I mean, I get to a point. Yeah. See, but I mean, that's what if things get into the digital domain, there is actually, if you ask me, yeah, a lot of things can anyway be done. But when the moment you start to get into the pure analog, that's where the problem happens. That's where, because you're bound to go with the component property than any of the post corrections which come in. I think that's where Meyer Sound is actually has worked a lot on in their technologies in working on. I've seen a lot of them working in extensive.
Okay, Sandeep, I think we'll just continue. Let's maybe focus more on the theory rather than sharing examples. Maybe some bit of.
So all these filters, especially first order or second order filters, they can be implemented using. So first order filters. So there are two kinds of things that can be done in hardware. One is what is called as passive systems, and one is active systems. So passive systems are typically those that do not have any power generation that is involved. So you typically have that with LRC components. Yeah, and active parts are those that involve magnification typically, and they would include amplifiers. Yeah. And the transfer function very clearly defines whether something can be implemented using an active device or a passive device. Yeah. So typically for designing your low pass components, you would kind of need stuff like inductors, which does not allow for sudden change of current through it. Yeah. So you could use stuff like LR circuits or C, which is there in parallel and so on. Yeah. So typically, you would use capacitors when you want to have higher frequency components because they will suddenly discharge. Yeah, and so you can use LRC components to implement all these filters that are there. Yeah, and that is something like even when you have drives, right? When you have the corresponding thing in controls, when you have drives, you have a lot of these PIDs inside the drive that is implemented in hardware. Yeah. But the point really is that since these are physical components, there is, if you want to implement, the thing, what decides how complicated a certain circuit is, that is decided by the order of the transfer function. That is the degree of the transfer function that you have. The higher the degree, the more the number of components that you have. Yeah. So when you have low degree transfer functions, they can be implemented by analog components. Yeah. And there you do not have the sampling, quantization, and all these other distortions that are introduced. So analog, when you can work with analog, it prevents those distortions from happening. And the degree increases, yeah, then creating bringing in so much hardware to implement that kind of becomes more complicated. Yeah, but yeah, there are systems that have very interesting, that have been built using hardware, using analog, that are very interesting. For example, if you remember the Zoo-23 gun that we had in L&T at that time, that was quite. They had
Absolutely.
Yeah, it requires a lot of very interesting mechanical engineering to be able to pull off analog design.
It requires a combination of very, very intricate mechanical engineering and also very intricate math.
You see, the mathematician will give you an equation and will probably tell you that you need this many of transistors, this many.
Correct.
But yeah, put that on a board without causing electromagnetic interference and everything.
Basically there is a limit to which you can go analog in terms of ideally speaking, you would want to implement everything in hardware, but of course, there would be an obvious limitation because of some factors.
Yeah, yeah, true. That's
Ram sir, you had some point to make?
No, I'm okay. Thank you.
Yeah, Srini, sorry.
Okay, let's Srini carry on.
yeah. So so something that share some other stuff. So for example, I'll just show some stuff that happens here.
Srini, one small point. We have actually it's gone past almost about 80 odd minutes. May I request you to maybe come to like a taper down in the next 5 minutes if it's possible, and if at all we have some more things to discuss, we can always invite you back for a future session, because the topic is very vast, and of course I don't want you to dilute anything from your side. So if you feel that you need to taper down right now, you are free to do that. I leave it to
Do
you.
that.
I leave it to your discussion.
Sure. So the last thing that I need to tell is so what happens is that many times you combine a lot of filters, right? So for example, suppose you want certain high frequency components to be heard, certain low frequency components to be heard, you will connect a high pass and a low pass filter in parallel. Now there is an important thing that happens here. You see that the phase always tapers off more than the frequency. Yeah, so which means that even if so when I want to get a flat frequency response, when I interconnect filters to get a flat frequency response, it might not result in a flat phase response. Yeah, which would mean that although your amplification is uniform, you start having delays. You'll have certain distortions that are introduced because of delays. Similarly, when you want to have a flat phase response, you would have certain distortions that are there because of different amplitude responses. Your amplitude response need not be flat. So that is always a problem that you will have when you combine filters. Yeah, when you combine different filters, you will always have a problem of it's trying to make both frequency and phase responses flat is like trying to fill air in a balloon with holes. Yeah, so that kind of becomes slightly difficult, and that is like the big problem that is involved. And maybe we can have a separate talk on that some other day. So I'll kind of end it here on that note. And it was great fun talking here.
Thanks a lot, Srini. Are there any questions from the audience right now? Like, I think we perhaps like covered a lot of topics, and I think while the let's say the topics were quite let's say at a very slightly higher level, I hope that they were well understood. And if there are any questions which the audience has, they are free to ask Srini right now. Please unmute yourself and ask if there are any questions. Thank you.
Hello, Srinivasan sir. My name is Amit. I have a very small question. I understand the concept that there is a difference there is going to be an issue when we are trying to get a flat frequency response against a flat phase response. But I would like to know in which frequency band for the human hearing would this phase shift or mismatch in the phase and the frequency response be very clearly audible?
I don't think that depends upon the frequency per se. I mean, see the frequency band in which it's audible. The moment you have phase distortion, you will always have the signal spread over a larger time amount. Yeah. So that would just replicate the frequency response of the human ear. So the frequencies that the human ear hears well, it is those frequencies that you will also hear the distortion with. The frequencies that you don't hear well, those frequencies you won't hear the distortion also.
Okay, so it will be equally noticeable across the entire band.
Yeah, it will be noticeable proportional to how much that frequency is noticeable. The very low frequencies anyone here does not hear. So even distortions there you may not hear. It's like if I cannot hear a certain signal, if certain frequency, and then there is a delay in that frequency, you will not be able to make that out.
Okay. Thank you very much.
Thank you, Amit.
Srini, I have a question.
Yeah.
Actually, from the psychoacoustics point of view, the low frequencies need more integration time, something like
Yes.
30 milliseconds and all. So there
Yes.
probably like, things are not so badly audible. And because there's a long time span allowed by the brain to integrate, and maybe higher frequencies, this sort of things will be more audible. Is there something with the difference between how you treat the low frequency and the higher frequencies?
Possible. I don't really know much about this, but yeah, that should make sense. Anything that it's something that you need to take into account the frequency response of the human brain and ear and everything, I guess.
Ramsar, there is this particular theory. I'm also forgetting the name. There is a particular plot of the standard human ear, right? Like how the human ear perceives hearing. What is the name of that plot?
Fletcher-Mansunko?
Fletcher,
Fletcher
exactly.
Mansunko?
Yeah, Fletcher
Yeah,
Mansunko, exactly.
yeah, they only mentioned about the amplitude.
Exactly. Yeah,
But what I'm talking like, how you perceive like, the low frequency, what is the perception like, of the time errors, like, in the low frequency and the high frequencies. What is how so psychoacustically, they may not perceive both, in the same way.
But if you see the Fletcher
Because the low
Mansunko,
frequency, like, they need like, more indication. That's amplitude strictly.
no, but
Other one is
Fletcher
like, more
Mansunko also
indication.
talks about, hey, on one side you have the SPL level, and on the other side you have the frequency, right? On the Fletcher Mansunko. So against the frequency, it gives you
but
how
there
the
is no
human.
time. There is no
Sorry?
time.
No,
There
it's
is no
not a
time
timing.
there.
It's a frequency dependent. So in that sense, it gives you how the human ear perceives, and typically, as you correctly pointed
Yeah,
out,
human hearing is
it's
not linear.
yeah,
Human
it's not
hearing is not
linear.
linear.
It's more
Yeah,
sensitive
that's
at
it.
certain frequencies, and it is less sensitive at
Right,
certain other
right.
frequencies.
Yeah, we are looking at the time domain now, what happens, what
Right.
you can make out in the time domain and what you cannot make a time domain at various frequencies. So low frequencies, need more integration time. So probably like,
Correct.
we are more tolerant to time errors. That's my
Correct.
understanding, but Srini can tell us like, more about it.
Yeah, you're fundamentally right.
Yeah, that's perfectly right. Yeah.
Thank you. Thank you.
Okay, I think Russell, is there any question from your end?
Not really. Thank you.
Great. Okay, I think with that, Srini, I think we'll come to the close of the session, and if there's a request from the audience, we'll probably call you back for a future session for some other topics also. I think
Sure,
by
that'll
and
be a
large,
great idea.
Yeah.
Yeah, sure, that'll be great.
Yeah.
Yeah, thank you very
Yeah,
much.
exactly.
Thank
So
you.
we could also take it offline, or let's say, depending on the nature of the questions which come from the audience, maybe to me separately offline, we could either take it up as a separate session, or we could address them, let's say, one by one, depending on the nature of the questions. So I'll come to that a bit later. So I think with that in mind, we'll come to the close of the session. It's been a very, very educative and very, very interesting discussion that we've had. And
Yes.
I want to thank Srini from the bottom of my heart, because, as I always maintain, some of these topics are very deep in nature, and there is a basic level of math which is required to understand some of these concepts, which I would say that it is highly desirable. But of course, a lot of us get bogged down by the math. So yeah, we just like to skim around the surface and try to not pay too much attention to the math. It can get very difficult because of, let's say, the backgrounds that each of us come from. But nevertheless, I think Srini has done a fantastic job in trying to simplify the topics to a level at which each of us could understand. At least I put myself in the shoes of a layman, and I could pretty much understand everything that Srini mentioned. And I hope that this everyone else also took it in the same spirit, because and I hope that that's the response from everyone. So having said that, thanks once again, Srini, and I look forward to a future session once again with you. We'll decide depending on the feedback that we get from the others. So
Srini, thank you very much. Thank you very
yeah.
much, Srini. We appreciate that. Thank you. Thank you.
Thank you so much, and I will end the session right now. Good day to all of you. Good day. Good day. Bye.